I'm Yonggang Jiang from Max Planck Institute for Informatics. I'm going to talk about this paper, Finding a Small Vertex Card on Distributed Networks. This is a joint work with Sagnik Mukhopadhyay from the University of Sheffield. Let me first introduce the computation model. We're using the congested model, so there are n computers. Each computer has its own private memory space, and there are some communication channels connecting some pairs of the computers. This is formalized as an undirected graph, where each node initially only knows the information of adjacent edges. And the communication happens in synchronized rounds. So that means at round 1, each computer will prepare some message to send across the communication channel, and those messages will arrive at the destination at the same time. The message size is required to be log n. And we also assume that there are unlimited local computation at the end of each round. So at the end of round 1, those computers will do some arbitrary computation based on the message received in the last round, and then prepare some message to send to other computers at round 2. And the complexity is measured by the number of rounds, so that means the local computation is free. And the goal is usually to jointly compute something at the end of the computation. And this is a problem we're caring about. We want to find a small vertex card in the network. So what is a vertex card? So vertex card is defined as a vertex set that removing it will disconnect the graph. So for example, this is a vertex card. And the formal definition is given k, where k is input for every computer. And they want to decide whether there exists a vertex card besides k or not. So our algorithm can also handle the case where a vertex card should be an output, but for the sake of simplicity, let's just assume they want to decide whether there exists a vertex card or not. And our algorithm only works for undirected vertex connectivity. And here are some histories about this paper, about this problem. So back to 1997, there is an algorithm that runs in d plus root n time, but it only works for k equals 1. And in 2011, there is also this algorithm that only works for k equals to 1. And in 2014, there is this algorithm that works for any k, but it's a log n approximation. In 2019, this is the first algorithm that works for any k, but the running time is quite inefficient. It's exponential in k, and also this delta is max degree, which means it can be as large as n. And recently, there is this paper that come up with the algorithm runs in d rounds, but it only works for k equals to 1 and 2. So basically, there are no sublinear algorithm before our paper come out, or even for k equals to 3. So our paper gives a sublinear algorithm for any small k, and it has running time k to the power 3 multiplied by d plus root n. So here is the summary of the history, and just to mention, our algorithm is randomized. So let me first talk about some open problems. The first one is to get a better algorithm than our paper. So basically, there are no lower bounds for unweighted vertex connectivity. So that means it's still possible to get better than root n plus d algorithm for vertex connectivity, at least for some small k. And the second open problem is to get a sublinear round algorithm for arbitrary k. Our algorithm is quite inefficient for a very large k, like k equals to order n. And it is a very interesting question to get a sublinear algorithm in this case. And also in parallel and streamline or some other models, the vertex connectivity is still quite open. And it will be interesting to see new algorithms coming out in these models. The rest of the talk will be focusing on the technical part of this paper. So first, we are going to talk about the sequential algorithm idea. The sequential algorithm idea is borrowed from the paper from 2019. So suppose this is an undirected graph, and this set S is the vertex card, the minimum vertex card we want to find. After deleting this S, this graph will be split into two sides. One side is smaller and one side is larger. This is called L and this is called R. And there are some assumptions made. The first one is that we know the size of L roughly, and this assumption can be removed by guessing the size of L from 2, 4, 8, 16, etc. Second assumption is that S is quite small and constant. So this S refers to the K, and as we said, our algorithm only works for small k, so that is also a reasonable assumption. To extend it to larger k just needs some more efforts. Okay, and the sequential algorithm works roughly as follows. First, we sample each node into a set R with probability 1 over L. And with that probability, it is guaranteed that with probability at least a constant like 0.1, the sample set R will have exactly one node in L and no nodes in S and all other nodes in R. And with that guarantee, we can find this set R's by the following procedure. Like for each node U in R, we do find a minimum vertex cut to another vertex V in R. So if we can find the minimum vertex cut between U and V, then we're done. And finding a vertex cut can be done by running augmented paths just like MaxFlow. Just by running k times of the DFS, it suffices to find the minimum cut set S. And by running augmented paths, I mean to run the DFS in this way and until it reaches another node V. And in the next iteration, the DFS should not visit the vertex twice. So if it reaches the vertex, it is forced to come back and then continue the DFS. And this is considered augmented paths. And that is just to guarantee that we are maintaining an internal vertex disjoint path all over the way. So after k times, we will get k internal vertex disjoint paths, which is a certificate that S is larger than k. And if not, then it is certificate that we already find a small vertex cut at less than k. So this is just identical to the MaxFlow algorithm. But the question is, this algorithm is quite inefficient because every augmented path will have length n, and this is not what we want. And a main contribution of this paper is like it discovered that the DFS just need to explore k times L vertices. And after explore k times L vertices, we just need to pick a random vertex as the destination among those vertices. For example, it can be this. And then we just take this as the destination and take this as the augmented path. And the key point is that by doing this, we're guaranteed that with probability at least 1 minus 1 over k, the destination will be in R because we sampled from k times L vertices and the size of L is just L. And for k times of DFS, all of them will have destination in R with probability 1 minus 1 divided by k to the power of k, which is a constant. So basically with constant probability, the algorithm will succeed. And if you look more into it, it actually has one-sided error, so you can boost it efficiently. So that is basically the sequential algorithm idea. So let's see how to implement it in congest model. So there is a trivial idea to implement this algorithm in congest model. Let's first revisit the algorithm. So the algorithm is basically about you have n divided by L vertices in R, and you want to run k times of DFS to find augmented paths from this n divided by L vertices. And the DFS will terminate if one of these conditions hold. The first one is that it reaches another node V in R, or it has explored omega k times L vertices. And the basic idea to implement in a congest model is to run this DFS simultaneously for any node in R. So there is a paper by Ghaffari in 2015 that said simulate n divided by L algorithm, which are those k times of DFS. You just need to do it in congest model in congestion plus dilation time. So for those who are not familiar with these concepts, the congestion is the maximum congestion of each edge, where the congestion of an edge is defined as the number of messages sent by all algorithms through this edge. So in our case, it's n divided by L because for any edge, each node in R will run this DFS and send a message at most constant times through this edge. So if you have n divided by L vertices, the congestion will be n divided by L. And the dilation is to just define as the maximum round complexity for all the algorithms. Like in our case, it's K times L. That's because after exploring K times L vertices will just end. Okay. And now we can see the obstacle. So basically, if this L is much smaller than root n, then we have a high congestion because n divided by L is super large. So we have a lot of nodes in, or a lot of vertices in R, and those vertices will cause a large congestion. And when L is omega root m, then we have a high dilation. So that means each node needs to run DFS for a long time to finish. So we'll talk about how we solve these two obstacles later. Okay, so let me first talk about how we solve the first obstacle. Just to remind you, the first obstacle is about we have n divided by L vertices, where L is pretty small, so we have too many vertices, and all of them want to run DFS k times to find augmented paths, and that causes a large congestion. An important thing to mention is that augmented paths depends on previous explored edges PU. What does this mean? It's like this node U use the first iteration to get augmented path, which is called PU. Then in the second iteration, this orange path, once reach a node in PU, it is forced to go back in order to maintain a vertex disjoint passes. There could be another vertex V which has different PV. Also, it's trying to find augmented paths denoted by this red edge. And they somehow reach the same point, and that will cause a congestion. So to solve this problem, we prove the lemma. The lemma says if they met at this point, then just by using PU, PV, and the augmented path of U, which is the orange edges, and the augmented path of V, which is the red edge, and just by using those edges, either U can find the path to V or V can find the path to U, and they should be augmented paths. So in this example, basically this node V can find the augmented path to U in this way. So here is how we use this lemma. First, we denote all the edges we just described about as HUV. And the algorithm works like the follows. So if the DFS of W is some nodes that we want to run DFS, never met other DFS, then there are no congestion and this DFS can just stop in K times L rounds. So like this, and explore K times L nodes and randomly sample a node to stop, and yeah, that finish one round of DFS. But if some node U meets another DFS of V, just like we described in the last slide, then they just stop the DFS. And then they use this HUV, which is all the edges here, at size K times L, to start a new DFS. For example, U start a new DFS to find augmented paths by HUV, and we also start a new DFS using HUV to find augmented paths. And in this way, this node V will successfully reach another node U, which is a valid augmented path. And then this node V just finishes tasks, and this node W also finishes tasks. And by this way, each iteration, we will eliminate at least half of the nodes to finish their task. And by running log n iterations of this procedure, we will find augmented paths for any U in R. There is just one more thing to mention. So HUV can actually intersect for different UV pairs. So what does this mean? If this is the HUV, it includes the HE. There could be another UV pairs, which is U prime V prime, HU prime V prime, which also includes this HE. And basically, we don't want this HE to be included to too many HUV pairs, because if there are too many, then the congestion is still super large. The observation is that each round this edge E can be included in just one more edge U width, because remember that edge U width is defined to be the joined edges jointly as the PU, PV, and the augmenting parts of U and augmenting parts of V. And in each round, each edge can be included in at most one of them. And in total, there are k squared times L rounds, because they want to do k times of DFS, where each DFS runs for k times L rounds. So basically, we know HUV has the congestion k squared times L. Let's talk about the second obstacle. The second obstacle is when L is very large, like as large as n. Then if this node U want to find augmented paths, the path will be as large as n, so it will cause a very large dilation. The first observation is that augmented paths is just like finding directed paths on a directed graph, where the directed graph is defined by PU. For sake of simplicity, let's now consider the directed paths as many paths directed to U. The real situation could be more complicated, but this should be a very similar case. So let's just consider this case. So let's say we just want to find a directed path on this specific directed graph that defined by PU. And there is a very long history of reachability on directed graph. And the state-of-art algorithm is this, very close to root n plus d, but it is not exactly root n plus d. It is slightly greater than root n plus d. And our contribution in this part is to give a reachability algorithm on the directed graph defined by PU, which is a very specific directed graph. That directed graph contains k paths, k directed paths pointing to U, where all the other edges are undirected edges. And our running time is root n plus d. Okay, here is how we do this. So the first observation is that reachability on undirected edges is easy. So we just forget about all the undirected edges and only focus on the reachability on this PU, where that contains all the directed edges. And just as all the reachability algorithm, we first build a virtual graph, where the virtual graph contains root n vertices. And the virtual graph should preserve reachability, and each node is root n far from the virtual graph, like this. And now the problem is just to find the reachability in this virtual graph. The crucial part is that we show we can sparsify this virtual graph to have only k times root n edges. So in that case, we can just broadcast this graph efficiently, and each node can just locally compute the reachability in this virtual graph. And the idea to sparsify the virtual graph is that we only need to preserve edges pointing to the farthest node from U in each path. So what does this mean? For example, node 1 has two edges to node 2 and node 3. But since we can do some pre-calculation to tell us that node 2 is closer to U in this path than node 3, so we know that node 3 anyway can reach node 2, and we can just delete this edge and just preserve this edge from 1 to 3. And it will automatically point to 2 by the path from 3 to 2. So in that case, we can restrict the degree of each node to be k, and that will specify the virtual graph to have k times root n edges so that we can broadcast it. That's a rough idea. There is just one more issue to mention. Remember that we have n divided by L vertices in R, so we actually need L divided by root n congestion instead of root n congestion. And the observation is that the size of PU is actually k squared times L. So by running reachability on PU, we actually can achieve L divided by root n congestion and k times root n dilation. Because these two numbers multiplied together, it will give you this number. And just to mention, this is a very rough outline of the algorithm for large L, and the whole algorithm is more complicated than that. But I hope this will give you a rough idea of the intuition why this can be solved in root n plus d time. Okay, and here is the summary. We give a congested algorithm which runs in k to the power of 3 multiplied by root n plus d time for vertex connectivity. And here are some open problems for future research. Thanks for your listening.